Test. Yes. So I've been mostly dealing in geography in various increments in various fields. I'm part of the Royal Geographic Society. I'm part of the Explorers Club. As I said, I'm also part of the Austrian Space Forum. Right now, these days, I'm a director, founder of Creation Space. What we do in inspiration of the activities of analog research is we are locating technologies, entrepreneurs, people, researchers that have no clue that what they're working on is relevant for space exploration. And like a dealer, we get them addicted slowly. And we're also able to get investors addicted to this. So we get knowledge and we get funds together in order to get them start developing for space exploration. Initially, of course, orbital, because this is more relevant for investors, but we already have a half a ton slot on the next Starship launch to Mars, which is right now scheduled for 2030. Probably many are skeptical about the timeline, but nevertheless, we are starting to develop the first technological demonstrations from our activities to Mars, already at this point. But as I said, I'm not going to talk about Mars, I'm going to talk about something entirely different, and also an activity that has been inspired by analog research. When I said, hey, well, using an expedition as a platform for doing research and technological demonstrations for future Mars missions, why don't we do those kind of expeditions that are open for whoever wants to demonstrate and research anything anywhere on Earth? Why don't we do this for the purpose of our life today? So this is where I started this program. By the way, this is me, right? Of course, the right part, not the left part, because I'm not American. And what we did, we started to establish expeditions as platform for the technological demonstrations and research for citizen scientists, for entrepreneurs, for very low TRL level technologies, just in the sake of providing them a platform to mature their technologies and research. In general, what I'm going to share in the very short time we have is why we choose Svalbard specifically for the expedition that I'm going to discuss about. A little bit tell you about how did we design the expedition and why did we make the choices of doing the expedition and why one way over the other. A little bit talk about the results. And mostly I want to deal with the challenges. This is, I think, where we'll find all the similarities and the relevance for Mars exploration. If it's okay, I want to deviate a little bit from the protocol. So if anyone wants questions and remarks, jump like popcorn. Okay, don't wait for the end. And I'll be happy to if this could turn into a discussion. So, why Svalbard? Svalbard is located at anywhere between 78 to 80 degrees north. It's pretty far up north. And this has implications on the location services. First of all, because of the availability of communication to satellite infrastructure for the GPS, GLONASS, and other GNSS networks. There's ionospheric disturbances in the pole because of the effects of the magnetic field and radiation that is penetrating, and of course the distance that communication has to do through the atmosphere until it reaches the end user on the surface and back. And also there's a very limited infrastructure in situ on the ground to allow the positioning to be as accurate as we are used to get it where in population centers around the world. Also the harsh environment, minus 40. I've flew to Svalbard when it was around plus 40 degrees in Israel, and within 24 hours I've reached minus 40 degrees. I think it's almost the exact delta where you have in the equator on Mars, which I've pretty much appreciated this delta at the first point, but after they started to drill down to your skin, into your bones, and start to be very, very difficult to handle. Winds, there's a very important factor of how winds cause erosion on the equipment that we're being able to carry over there. Not comparable to Mars in terms of the speed and of course the pressure, but if you take the particles that are carried by wind on Mars and the amount of damage they can create, in order to do this on Earth, you don't have those particles available in every environment. So increasing pressure and wind, of course, creates maybe some similarities. Whiteout, sastrugies, which are snow forms that are creating very difficult terrain to cross, and you'll see soon how we're going to cross it. We chose to do this as a mobile science platform, and I'll explain soon why. And this has a lot of implication about how do we do the science, how do we schedule the science, and how do we manage the balance between our traversing, our traveling, how much time we invest in science, and how much do we care about our well-being while we do this. And of course creates many measurement challenges that are reminiscent of what we'll probably find on Mars. And of course there's lots of operational constraints that the Svalbard environment puts us through. A little bit about the experiments that we've been taking. We had two main technological demonstration experiments, which their aims was mostly to accelerate their TRL. They were both very early stages at the time. They were onboarded at around TRL 4. They reached TRL 5 before the expedition, and on the component level, we've been able to test the components for TRL 5. Afterwards, you'll see the results. There's another research, academic research that we supported, which is the GRASP one, which was one of the first steps in trying to measure cosmic particles on a mobile platform, specifically in the region that we've been in. There was one small-scale research that has joined on the last moment of preparing to this expedition, which is Naked Pack, edible food packaging. By the way, opening a side note here, they developed this package in order to decrease waste. And the only problem with having a package that you are putting on the shelves in a supermarket that you're going to eat later, that it undermines entirely the purpose of the package to get the food contained from contaminations outside, because you eat the package with the contaminants. So they actually, what they found out is part of the support we're giving them, that their use case is actually more relevant for exploration and for B2B, B2G activities rather than to B2C activities, meaning oil rigs, expeditions, space, of course, etc. Two educational programs. We've supported the NASA Globe initiative, if someone is familiar, and if not, I can elaborate about it a little bit later, and an outreach activity for young kids where we do immersive storytelling. Again, I can expand if you wish. I don't have slides about this because I want to focus on the challenges. So this is the route that we chose to take. It's relatively varied. So you have your valleys, you have here mountains, you have here glaciers, you have here rocks, you have here narrow valleys, big valleys, canyons, and we try to get as much variety of terrain as possible. So we can challenge the systems, mainly the positioning systems that we were carrying, with variety of obstructions for the line of sights. As I said, those two technological experiments, we've tried to get them to the TRL 5 stage, also doing for one of them an actual on-site acceptance test following a pre-written protocol. and also serving as kind of a contracted research organization for the edible packages experiment. We've been utilizing space assets, again, not the GNSS satellites, but we've been using a lot of signal of opportunity for one of the positioning experiments that I'll be able to elaborate later. 11 days out there in the field, 12 people, and what we were planning to do is a daily routine of 8-hour travel, 8-hour logistics, and 8-hour sleep, where priority is given always for sleep. Because of various reasons, ability to acclimate to the cold and function and safety, etc. Every participant has been carrying, of course, the thermal equipment that he needs to survive in these conditions, skis, poles, and has been carrying his all personal equipment with some of the crew's equipment divided in between the poles, the sledges. There's an estimate of around, depends on the capabilities of each person, of around between 30 to 50 kilograms per person that is being carried over the snow. Every stop, every camping, we've set up a camping site where we've been sleeping 2 people inside each tent, constantly rotating between the people that are sleeping in the tents. And this is where we dried our equipment, prepared food, melted water for the next day, and mostly, this is where we mostly did the research and the experimentation. Inside the tents and when possible outside. During the night, we've set up a perimeter around the tent of flares against bears. Yeah, we're carrying rifles. We're doing night shifts as a bear watch. This is not something you'll probably have to go to do on Mars, I hope. And here are the results. So we have the research, the academic research, trying to collect cosmic rays readings. This had a complete systematic failure, and I will explain a little bit more about this later. The 2 positioning demonstrations have succeeded. This one, we followed the complete acceptance test procedures that we probably managed to succeed at around 90% of the tests. The North Starlink was also not following a protocol, but it generates precise position without using any GNSS infrastructure. And naked pack, a material failure, which is the comedic part. I will follow on this later. What is interesting, however, is how we conducted in comparison to what we've planned. So we've been planning to do an 8-8-8 mechanism where we prioritize sleep. And as you can see, we did not prioritize sleep for some reason. We constantly made the decision, okay, let's walk a little bit more, let's do a little bit more research. Because as you see here, the time we were able to invest in doing research activities was so limited because of all the logistical constraints and all the operational constraints that I did not mention earlier, just as a headline. And here I'm starting to dive into the challenges. Before that, what did work is that we've shown a predeterministic improvement as we progressed along the expedition. Let me know how much time I have.
Well, not a lot.
Okay. We had a lot of in-situ decisions that we had to reroute and, of course, deprive ourselves of sleep. Mostly all the preparations, the physical training, the team building activities beforehand and things. And having in the field PIs who were very familiar with their payloads, this is eventually what helped us succeed in at least 2 experiments over there. So challenges. So as I said, sleep has dropped to around sometimes even 4 hours a night, mostly because we did not took into consideration the bear watch and the change between shifts in bear watch. And also, storms have deprived us of sleep because in at least 2 nights we had storms that brought enough snow to make the TADs collapse on us, and we had to dig ourselves out. So it turned out to a full 4-hour excavation mission at some point. Night observations. There was a lot of value for the night observations. First, because we were lucky enough to get quite a lot of aurora events, which were very interesting for the cosmic radiation experiment. And also, eventually, one of the main conditions for the Jumptartic experiment was to test it every night, because the sensor was mostly looking at the sky at night. And soon, I promise you, I'm going to speak a little bit about the experiments themselves. Mental fatigue. Do you remember the 3rd quarter? So we had the 2nd, 3rd, the more drop down, and you can actually feel it all over around you. How everyone energy starts to drop. You can actually see it in the graph. Where we started concentrating on the walking, on covering distance, because this is the only thing that has actually helped us feel some kind of efficacy. And this is reported by People journals, that the only thing that helped them feel a little bit better is by changing scenery and covering a little more distance, despite it was taking more time from the science itself. So for the Jumptartic, this is the Jumptartic experiment. These are 2 sensors, 3 sensors actually, looking to the sky. The main sensor, the primary sensor, here is a shortwave infrared. And what they were doing with the sky observation, they were trying to analyze celestial bodies, satellites, space debris, and triangulate just by observing the sky. It has a connection. It was continuously connected to the internet through a Starlink, to a database, to an almanac back at the back office, who was able to make the calculations. Lots of artifacts that he needs to disregard by looking at the sky and identifying those objects just by the pattern they move and the relation between those objects which are not artifacts. Very complex computer vision technology. The main challenges were that battery life in deep and very extreme cold is very difficult to handle. Before you operate the battery, you need to warm it up. So you either takes you a lot of time to start running an experiment run, or if you want to do this fast and efficient, you're going to give away a lot of battery time, a lot of battery capacity. Because the battery is not warm enough. The large power banks that we're aiming to take, they could not arrive because regulation. We cannot fly over battery packs of over 100 watts per hour, and they were not going to make it on time by naval shipping. The experiment eventually, because of our concern with battery life, took a lot of time to set up. Every time we wanted to do an experiment run, and this is why we probably took exactly the amount of data that we required with no redundancy, because it was just too long to set up. We cannot do this in breaks. We can only do this while we were camping. Lens obstructions, snow particles, and condensation icing around the lenses, also something that interfered quite a bit, and it's really a headache to clean it because you don't want to scratch those lenses because of the resolution is part of the secret sauce of this sensor, and everything had to be manually operated. Lots of lessons learned here that we're going to follow up on future expeditions. North Starlink. So this one has been collecting signals of opportunity from a variety of satellite communication infrastructures, Iridium, Inmarsat, Starlink, etc. And if you are familiar with those challenges, yeah, the challenges are the same. One of the problems with this system was that it had to be stationary every time we collected. So it was a little bit faster to deploy. So he managed to do this while we were walking, but you cannot let it run while we were moving. We'd have to dedicate at least half an hour of every break we made along the way to allow the PI to deploy his system and collect data. Lots of artifacts and interferences because of lots of communication and packets running all over Svalbard from a variety of the directions that are not signals or opportunity from satellite infrastructure. His laptop failed because of the cold environment, so we had to eventually to rely only on one rugged laptop that I will mention soon. And of course the gloves, operating a laptop with the gloves, you know, it's not gloves, these are actually mittens. Pretty impossible. So lots of user interface lessons learned here. Grasp. Again, I'm going to concentrate on this one, okay? Look at this switch, trying to operate this with a mitten. Luckily, I like to eat with chopsticks, okay? So, and on the other side of my chopsticks, I've got multi-use chopsticks. There's rubber parts that it was easy to turn it on and off. But the amount of time it required to set it up, because I had to take my laptop, take out the battery, put it inside my jacket, warm the battery for 20 minutes. Once it's warmed up, I need to reconnect it to the laptop, all with mittens. Then take a USB cable, connect it to the laptop with mittens, then collect the other part of this USB with the mittens to a mini USB here, which is even more difficult. Then with the chopsticks, turn on the sensor, and this entire process probably took around 40 minutes to an hour just to start collecting data. And once it's collecting, it should be stationary because every movement would have interfered with the collected data. As you can see, this is pretty makeshift. Make it back. So we took 3 samples. 2 of them exploded in the airplane because of the pressure. Okay, so I had only 1 left. This package is composed of proteins. And the moment we stepped out to the cold, it immediately froze and broke. So again, the 3rd package also did not work as intended. And after I cooked it, this is how it looked. The package did not dissolve. So I think the worst part about it that the food that they put inside was terrible. A little bit comparison between temperature and how much science activities we've been able to do, running swiftly through this. And since nobody commented and asked questions, I'll wrap up. Important thing I want to highlight: sunlight. Super important for our well-being. It took us 3 days until we reached the first time we had sunlight touching our face. This had an immense effect on our physical capabilities and of course mental ability. Also humidity. It was very dry in the first 3 days. And when it's humid and cold, it's terrible, but the humidity also helped us a little bit, you know, feel life physically. These 2 are very basic elements in life, and we actually felt this. very, very aware of how important they were. The sense of purpose, people who had sense of purpose had the easier way to go. People without a sense of purpose who lost it on the way, of course, had a hard time to go. There were some people with an extreme sense of purpose which caused even more harm than good. And I can give examples later because I have no time. Archetypes, everyone tried to find his own position, and there were some struggles between different archetypes, but most importantly is the turkey. Thanksgiving, yeah. The ability to appreciate, I think this was a key for surviving and actually performing. The ability to appreciate where you are, what you see, the people that you are with, and the activity that you do, and every single little element that you can appreciate was a key performance indicator for this expedition. We have more expeditions coming. If anyone is interested, this is my LinkedIn. I can wrap up.
Sometimes when we touch here.
Yes.
Okay, yeah, so some questions. Last questions.
One question about the mission architecture. You are proposing like 8 hours, 2 times 8 hours. Would it be relevant to have another scale like 3 times 7 hours and 3 hours of, I don't know, practicing being lazy or lenient or having sport or doing anything else that is not related to? Would that have changed anything? According to you?
If anyone finds a research that involves practicing being lazy, please let me know. Okay, I would love to do that. The reason we did an 8-8-8 mechanism is because of the involvement of positioning systems. So we had to cover distance. And there were 2 constraints that we cannot play with once we move. All right? So there's the 8-hour sleep. We don't want to take away from that. And then there's the 8-hour logistics every day. And 8 hours logistics means packing up camp in the morning, approximately 1 hour, break every 45 to 1 hour to drink something because you cannot use a water tube. You need to pull your water from the bag, from the sled. You need to grab something to eat, so this also compiles to around 1 hour and a half. Then you have the science activities, at least 1 hour, 2 hours a day. The preparation of those activities. And the camp setup. And the camp setup is quite a headache. It takes a lot of time. And once you set up camp and you start doing the scientific work, you have in parallel, you need to melt water, prepare yourself food, organize your equipment, take your clothes off. We're talking about 3 to 4 layers of clothes. You need to hang everything in a small tent with another person so they can start drying. You need to dry them actively with a flame. And then you need also to brush your teeth, go out to do pee-pee. Lots of activities, and if you do not manage them on the 5 to 10 minutes level, then you're starting to lose a lot of time to do other things. Yeah.
So obviously sleep did suffer during your 2 weeks mission at the end, as you mentioned. That kind of situation will probably happen on Mars because it's hard to do science properly. How do you think we could incentivize people to take the rest despite them being overachievers and wanting to do the science? Because on a 2 weeks mission, even if I'm sure it was really hard, it's probably manageable. Over 2 years it's impossible. So how would you incentivize them to force 8 hours, and that's not negotiable?
Mm-hmm. So first we're talking about overachievers here. One way, and we're going to have this in the next Svalbard expedition next year, is to have sleep experiments. Once, and by the way, everything is mission driven. Even eating, I eat mission driven. Okay, I don't want to eat this entire porridge, but I have to. I'm mission driven because otherwise I'm not going to have enough energy. So having an experiment involving sleeping would be a good way to do this. That's one. And here my system engineers come to play. You need to have experiments that are taking as less toll as possible from the user. User interface is super important. You need to have experiments that are autonomous as possible. And since we did not get that here, we did not get a lot of experiments. If our systems were just a plug and play and turn on, and let them run while we're doing our brush our teeth things, then we'll be able to do much more well-being activities. Yeah.
And one of the NASA baseline Mars mission architectures is for small rovers of teams of 2 people who travel about 50 kilometers in a week. Do you think we can get lessons from this kind of mission about that architecture, doing field science rather than technology demonstration?
Just to understand, the question is whether we can do a mobile science architecture.
Learn about how to do mobile field science from this kind of expedition.
Architecture-wise, I don't think so. It's going on an EVA on Mars with a sled connected or robot connected to you. Intuitively, I think it's maximum a full day activity.
The proposal is it's a 1-week drive
Yeah.
in
So
a rover, and you travel 30 kilometers in a rover with EVAs from the rover.
Yeah.
Do you think we could learn from that? 'Cause it's obviously you don't have a vehicle, but it's still a similar distance and it's doing similar science.
absolutely. These are kind of activities that we can learn from Mars architectures to do better here. There's actually a Russian vehicle planned for Antarctica, which was a full massive mobile space station. So sure, the Mars narrative also can help fund those kind of things. Yeah.
I think I have one last question, perhaps. You talked about sunlight, okay? But sunlight, I think there are 2 things. There is the light, and probably there is possibly a little bit of heat with the I don't know if the sunlight comes just on your skin, or so. Are you talking about the light or the small heat you have?
Great question, because it pinpoints exactly the difference between sunlight touching you than light. And this is exactly the experience that we had. For the first days of the expedition, there was light. There was light half of the day, like 12-hour daylight, but the sun was covered. It was always behind the mountains because it was a very low angle, very low altitude. So we saw light, we felt light, but there was no sunlight, no line of sight with the sun. The moment we had line of sight, and I can really recall this specific moment when the sun rose up from the mountains and this little, section, slice of sun peeking out from the mountains, and we had this moment of sunlight, of line of sight with the sun, when it was actually touching our skin, our faces, as a remarkable event.
Okay, thank you very much. So this is the end of the... Yeah, thank you.